There is a wire inside your wall right now. You've never thought about it. You've never had to. It's been there your whole life, and for your parents' lives too, quietly doing the one thing it was born to do: carry electricity from the world outside into the world you live in. Copper. Reddish gold, ancient, almost boring in its familiarity. The metal of pennies and plumbing and Christmas tree lights. You pass it every day without a second thought. But right now, in boardrooms from Santiago to Shanghai, in government bunkers in Washington and Brussels, in the war rooms of the world's largest mining corporations, that wire is being discussed with the kind of urgency usually reserved for oil embargoes and nuclear standoffs. Because the world is running out of it, not eventually, not in some distant theoretical future, now. And the consequences of that shortage are already reshaping civilization in ways that most people will only understand when it's far too late to do anything about it. Let's start with a number: $13,000. That is what 1 metric ton of copper costs as of early 2026, up from roughly $8,000 just 18 months ago. That's a 50% surge in price for a metal that underpins virtually every piece of electrical infrastructure on the planet. JP Morgan's analysts have been watching this closely, and they've concluded that the market is heading into a refined copper deficit of around 330,000 metric tons this year alone. ING Group's forecast is even darker: 600,000 metric tons short. Bloomberg NEF calls it the beginning of a structural deficit that will define the next several decades. The International Copper Study Group, which earlier this year was projecting a comfortable surplus, has flipped its forecast completely. From a projected surplus of over 200,000 tons to a deficit of 150,000 tons, a swing of 360,000 metric tons in 6 months. This is not a market correction. This is a market awakening to a structural reality that has been building quietly for decades, and the alarm is now going off. To understand how we got here, you have to go underground, literally. Deep inside the Andes Mountains in Chile and Peru, inside the jungles of the Democratic Republic of Congo, in the volcanic highlands of Indonesia, the mines that have been feeding the world's copper appetite for generations are now revealing their age. Ore grades, the concentration of actual copper within the rock being blasted out of the earth, have collapsed. Historically, miners could expect to find 1 to 2% copper in the ore they extracted. Today, the global average has fallen below 0.7%. What that means in practice is catastrophic. To produce the same amount of usable copper, mining companies now have to process exponentially more rock, burn exponentially more fuel, hire exponentially more workers, and spend exponentially more money. The cost of wringing copper out of the earth is skyrocketing even as the quantity of copper available in any given deposit keeps shrinking. And the pipeline of new projects to replace these aging, depleted mines, almost non-existent. Fewer than 10 significant copper discoveries have been made in the entire world in the last decade. 10. For a resource that is about to become the most strategically critical material in the global economy. And this is where the story becomes almost absurd. You would think that with copper prices at historic highs, with demand screaming upward from every direction, with governments and corporations waving billions of dollars at anyone who can dig more of it out of the ground, the mining industry would be in overdrive. New projects announced every week, shovels in the ground across 5 continents, construction cranes on every mountain. Instead, what you find when you look closely is an industry largely paralyzed. Building a new copper mine, from initial geological discovery to the first day of actual production, takes 17 years on average. 17 years, not months, not a few years. 17. In the time it takes to bring a new copper mine online, a child born today will have graduated university, established a career, and possibly had children of their own. And that 17-year figure assumes everything goes smoothly, that the environmental review doesn't get litigated for a decade, that the local community doesn't resist the project, that commodity prices don't collapse midway through and kill the financing. In reality, some projects have been trying to reach production for 30 years. The Resolution copper mine in Arizona has been in development since the 1990s, has absorbed billions of dollars in planning, permitting, and legal costs, and as of today still has not produced a single ton of copper. Not one. Meanwhile, the mines that are supposed to be carrying the world are falling apart. In September 2025, a catastrophic mudslide at the Grasberg mine in Indonesia the second largest copper mine on the planet, operated by Freeport-McMoRan, triggered a force majeure and crippled operations. The Grasberg Block Cave portion of the mine, which accounts for 70% of the facility's previously forecasted production, went dark. As of today, in 2026, it is only in a phased restart, with full recovery of some sections not expected until 2027. At nearly the same time, in May 2025, a seismic event caused massive flooding at the Kamoa-Kakula complex in the Democratic Republic of Congo, one of the most important new copper projects in the world, run by Ivanhoe Mines. Production was revised sharply downward for both 2026 and 2027. Chile's El Teniente mine, the largest underground copper mine on Earth, was struck by seismic activity that sterilized entire production zones. The mine's general manager publicly stated that production would be depressed for the next 5 years. Quebrada Blanca in Chile also issued production downgrades. And then there's Cobre Panama, a massive world-class deposit operated by First Quantum Minerals that was shut down in late 2023 following violent civil unrest and legal battles with the Panamanian government. That mine alone, when it was running, represented roughly 1.5% of the entire world's annual copper supply. It is now closed indefinitely, its ore sitting in the ground, its future trapped in the courts. 3 of the biggest copper mines in the world went offline within months of each other. Wood Mackenzie's head of copper research said it plainly. Last year, the industry was beset by a number of big challenges. 3 of the biggest mines in the world went offline for a period. The new supply that was supposed to plug the growing deficit was significantly disrupted and deferred into future years. And because mine development takes 17 years, there is no backup plan. There is no switch you can flip. There is no emergency warehouse somewhere full of refined copper waiting to be deployed. When a mine goes down, that supply is simply gone. Now let's talk about what's happening above ground, because the story underground is only half the crisis. What has changed in the last 5 years, and what has changed most dramatically in the last 2, is the nature of demand. The world didn't just want more copper. The world suddenly, urgently, desperately needed copper of a kind and in a quantity that no one had fully planned for. The energy transition, which for years existed mostly in policy documents and press releases, began to actually happen, and when it did, it collided with the copper market like a freight train hitting a wall. Consider the electric vehicle. A conventional combustion engine automobile contains roughly 20 to 30 kilograms of copper. An electric vehicle contains 80 to 100 kilograms, 3 to 4 times as much. Automakers are planning to produce more than 30 million electric vehicles annually by 2026. Do that math. That's roughly 4 million tons of copper just for vehicle production, and that figure doesn't even include the copper required for the charging infrastructure. Each DC fast charging station requires 150 to 300 pounds of copper in its cables, transformers, and internal components alone. Now add the charging networks. Now add the grid upgrades required to handle all that new electrical load. Utilities across the United States, Europe, and Asia are undertaking the largest transmission infrastructure overhaul since electricity was first deployed at scale in the early 20th century. Grid modernization projects in the United States alone will require an estimated 5 to 7 million additional tons of copper over the next decade. Smart grid technologies, energy storage systems, distributed solar integration, every single one of these initiatives is copper-intensive. And then there's wind. A single offshore wind turbine contains 8 to 15 tons of copper in its generators, cables, and transformers. Offshore wind installations require up to 9,500 tons of copper per gigawatt of installed capacity. At a time when countries are racing to install hundreds of gigawatts of offshore wind, the arithmetic becomes staggering. Solar is copper-intensive too, approximately 3,000 to 5,000 tons per gigawatt. The International Energy Agency has concluded that renewable energy infrastructure requires 2.5 to 7 times more copper than fossil fuel technologies, depending on the type of installation. The very technologies we are deploying to escape our dependence on oil and gas are creating an almost unquenchable thirst for a completely different commodity. But here's the twist that almost nobody saw coming. The demand driver that appeared suddenly and is now consuming copper at a rate that has genuinely shocked analysts: artificial intelligence, data centers, the physical infrastructure of the digital economy. For decades, data centers were moderately copper-intensive, but not spectacularly so. Then AI happened. Traditional data center server racks operate at 10 to 15 kilowatts. AI data centers, the ones running the large language models, the image generators, the systems that the world's largest technology companies are racing to build, operate at 60 to 120 kilowatts per rack. That is a 6 to 10 times jump in power density. And in electrical engineering, when you pack that much more power into the same physical space, the current flowing through conductors increases exponentially. At those power levels, copper bus bars, thick, heavy copper plates carrying massive current, are not optional. Aluminum cannot substitute here. Copper's thermal conductivity of 385 watts per meter Kelvin vastly outperforms aluminum's 205. JP Morgan estimates that data center installations alone will consume approximately 475,000 metric tons of copper in 2026, up 110,000 tons from the year before. Microsoft alone has announced $80 billion in AI infrastructure investment. Google, Amazon, Meta, they are all building at the same time, and every data center they construct is a new copper vacuum pulling from the same depleted global supply. This is what analysts are calling inelastic demand. When a tech company needs copper to build a data center, the copper price doesn't stop them. The return on investment from AI infrastructure is so astronomically high that copper prices would need to rise to $50 per pound, from the current $5 to $6. Before these companies would pause construction, they will simply pay whatever is asked. And that reality, more than any other single factor, is why copper is being revalued not as an industrial commodity, but as a strategic digital asset. Now look at what the combination of all these forces, the dying mines, the absent pipeline of new projects, the insatiable demand from EVs, renewables, grids, and AI, has done to the physical market. China's top copper smelters in December of 2025 took the unprecedented step of collectively agreeing to cut production by more than 10% for the 2026 calendar year. This was not a business decision. It was a crisis response. Treatment and refining charges, the fees smelters charged to process raw ore, concentrate into refined copper, had collapsed to near zero, which means exactly what it sounds like. There is so little raw ore concentrate available in the global supply chain that smelters can barely find enough to run their facilities. The world's largest smelting industry, concentrated in China, is operating below capacity, not because there's no demand for refined copper, but because there is no ore to smelt. The physical ceiling on usable copper entering the market is not theoretical. It is here, it is now, and it was visible in real time when every major smelter in China simultaneously agreed to slow down. And here is where the geopolitical dimension of this story becomes impossible to ignore. China controls 50% of global copper refining capacity. More broadly, it controls 85% of global critical mineral refining capacity. And China has already demonstrated, clearly and deliberately, that it is willing to use this dominance as a geopolitical weapon. In 2025, Beijing tightened export restrictions on graphite, antimony, and certain rare earths in direct retaliation for U.S. trade and technology policies. The message was unmistakable. We control the processing of the materials your economy depends on, and we are not afraid to use that control. Meanwhile, mineral-rich nations are learning from this playbook. Chile and Peru, which together represent the largest concentration of copper mining in the world, are demanding higher royalties, greater state participation in mining projects, and more control over their own resources. The DRC has imposed export quotas and bans on cobalt. The pattern is clear. The countries sitting on top of the world's copper deposits are beginning to coordinate their leverage in ways that echo the OPEC oil shocks of the 1970s. And in the background of all of this, a strange paradox is playing out that tells you everything you need to know about who is actually winning and who is losing in this new commodity world order. As of late March 2026, global copper inventories across the London Metal Exchange, the Shanghai Futures Exchange, and the COMEX stand at over 1.1 million metric tons, the highest level since 2003. On paper, that sounds like there's plenty of copper. In practice, it's almost meaningless. A significant portion of that inventory is held by sovereign wealth funds, technology companies, and national governments as strategic reserves. It is earmarked, locked away, not available for the manufacturer trying to buy copper for next quarter's production run. It is, in the language of commodity markets, exchange inventory without liquidity. The copper exists. You just can't have it. It belongs to the people who saw this coming and moved first. American manufacturers stockpiled preemptively in 2025 when President Trump threatened tariffs on copper imports. Those tariffs were eventually suspended, but the hoard remained. U.S. warehouses are sitting on hundreds of thousands of tons of copper while the rest of the world scrambles. J.P. Morgan describes the dynamic with surgical precision. This open arbitrage locks the excess inventory in the U.S. for now, while also working to attract even more marginal imports. The copper is real. It exists in physical space. You could take a photograph of it, but it has been removed from the global spot market by the logic of geopolitical hedging, and its absence from the market is felt everywhere outside America's borders as genuine scarcity. Now think about what this means for the projects that depend on copper. Not the theoretical future projects, the projects that are supposed to be happening right now. Offshore wind farms that were supposed to go live this year are sitting in construction limbo. The submarine cables, the onshore transformers, the grid tie-in infrastructure, all of it requires copper, and all of it is running into the same wall of material cost and availability. Smart grid upgrades across Europe and North America, the foundational layer of the decarbonization of the electricity system, are facing unmanageable material costs that are forcing project managers to delay, redesign, or cancel phases of work that were already contracted and funded. Renewable energy developers are operating on thin margins. Wind and solar projects are financially engineered to work at specific cost structures. And when the cost of copper blows past those assumptions, entire projects become unviable. This is what analysts are calling greenflation, the inflation generated by the very act of building the green economy. The transition itself is consuming the materials it needs to succeed. The electric vehicle market is feeling it directly in the form of price pressure that manufacturers are either absorbing as margin destruction or passing on to consumers as price increases that are killing the mass market EV dream. Battery-grade copper, the ultra-high purity material required for EV motor windings and battery management systems, has effectively decoupled from historical price norms. It is trading at a premium to standard refined copper as the specific grade required by the most demanding end users becomes its own scarce commodity within a scarce commodity. So what are engineers doing? They are doing what engineers always do when a primary material becomes inaccessible. They are looking for the next best thing, and they are finding it deeply unsatisfying. Aluminum. Aluminum is lighter than copper, it is dramatically cheaper, and in some applications, particularly high-voltage overhead transmission lines, where the low weight actually matters, it can serve as a functional substitute. Engineers are revisiting aluminum in wiring applications at a pace not seen since the energy crises of the 1970s, when the last great commodity shock forced similar compromises in electrical design. But aluminum is not copper. Its electrical conductivity is about 60% of copper's. To carry the same current, you need a larger wire. A larger wire weighs more, takes up more space, requires different connectors, different installation techniques, different long-term maintenance protocols. For the kind of high-density, high-performance applications that define the cutting edge of modern electrical infrastructure, the AI data centers, the EV powertrains, the high-frequency grid management systems, aluminum is not a solution, it is a concession. And for the infrastructure that was originally designed and optimized for high-purity copper, retrofitting with aluminum is not an upgrade. It is a downgrade with a longer lifespan and more failure modes. The long-term reliability concerns of substitute materials in copper-optimized infrastructure are not abstract engineering theory. Aluminum wiring in residential applications caused a wave of house fires in the United States in the 1960s and 1970s, precisely because of the subtle but significant differences in how aluminum behaves at junctions, under thermal cycling, and over long periods of use. The industry spent decades removing that aluminum wiring and replacing it with copper. Now, under the pressure of the 2026 market, some of that history is at risk of repeating itself. Not in residential homes, but in the billion-dollar infrastructure projects that are supposed to power the next century. There is one other avenue that everyone is talking about as the short-term solution, and it is genuinely promising, genuinely important, and genuinely insufficient on its own. Recycling, urban mining, the recovery of copper from end-of-life electronics, demolished buildings, scrapped vehicles, industrial waste streams. Copper is 100% recyclable with no degradation in performance. Recycling it requires 85% less energy than extracting it from ore. And the copper is already there, sitting in landfills, in e-waste streams, in the walls of buildings being torn down across every major city on Earth. About 20% of all copper scrap generated worldwide, roughly 4 to 5 million metric tons, never enters formal recycling channels. It is simply lost. If that recovery rate could be improved, if the infrastructure for collecting, sorting, and reprocessing copper scrap could be built out at scale, it would meaningfully reduce the pressure on primary mining. The IEA has called for mandatory recycling rates, improved sorting technologies, investment in secondary smelters, and strategic collaboration between industry stakeholders. Under the most optimistic assumptions, recycling could provide 35% of global copper supply by 2050, but that leaves 65% still dependent on mining. And mining, as we have established, is in a structural crisis that no recycling program can fix. S&P Global has done the most comprehensive accounting of where this trajectory ends, and the numbers are sobering. Demand for copper will reach 42 million metric tons annually by 2040, a 50% increase from current levels. Global primary supply, absent massive new investment, is projected to peak at 33 million metric tons around 2030 and then decline. The deficit by 2040 could reach 10 million metric tons of primary supply alone, on top of whatever recycling can contribute. To put that in physical terms, 10 million metric tons is more copper than the entire world currently produces in a year. And to fill that gap through new mines, an additional 10 million metric tons of annual primary production capacity would need to be built, requiring capital investment at a scale that has never been attempted, in timelines that the laws of geology and permitting simply may not allow. This is the moment that future historians will look back on, not as the beginning of a crisis, but as the point at which the crisis became impossible to deny. The world built an entire civilization on the assumption that copper would always be there. Abundant, accessible, affordable. Wires in walls, pipes in basements, windings in motors, transformers on poles. The metal of modernity, so ubiquitous it became invisible. And then, one decade into the most aggressive industrial transformation in human history, the simultaneous electrification of transportation, the replacement of fossil fuel power with renewables, the construction of a digital intelligence infrastructure of unprecedented scale, the world discovered that the one material it needed more than any other was the one material it had spent decades failing to secure. The nations that understood this early, China, which built its refining dominance methodically over 30 years, Chile and Peru, which are now demanding their piece of the value chain, the tech giants who stockpiled strategically before the squeeze, are positioned to navigate what comes next with leverage. Everyone else is negotiating from weakness, paying whatever price the market demands, accepting whatever delays the supply chain imposes, re-architecting whatever systems can be re-architected, and hoping that the combination of recycling, substitution, and eventually, new mines will be enough to keep the lights on. The wire in your wall is not going anywhere. It will carry the current that charges your phone and runs your refrigerator for years to come. But the wire in the next grid expansion, the wire in the offshore wind turbine being built to replace your gas-fired power plant, the wire in the EV you're planning to buy, the wire in the AI data center processing the world's information, that wire is contested. It is strategic. It is geopolitical. It is, for the first time in modern history, genuinely scarce in the ways that matter most. And the world that understood copper as background noise, cheap, reliable, infinite, is gone. What comes next will be defined by who controls the red metal, and the competition for that control has already begun.